A tiny 2-watt laser, actually weaker than the light in your fridge, has just delivered one of the most impressive communication results ever recorded in space, 1 gigabit per second sent from a satellite 36,000 kilometers above Earth. Honestly, this breakthrough kind of challenges everything we thought we knew about long-distance space communication. In this video, we're going to uncover how such a low-power signal managed to achieve such high speed, what technology made it possible, and why this discovery could really reshape the future of satellite networks. The most eye-opening part of this achievement is, well, the distance involved. A satellite positioned in geostationary orbit, which is roughly 36,000 kilometers above Earth, has successfully transmitted a 1 gigabit per second data stream using only a 2-watt laser. This power level is surprisingly low. It's actually comparable to the output of a small household LED indicator. Yet, despite the minimal power, the transmission reached Earth with enough clarity to decode high-speed data from one of the farthest operational orbits used for communication. And that's pretty notable, because geostationary satellites face a major challenge. The signal has to travel a much longer path than low Earth orbit satellites, which operate under 600 kilometers. Over such a long distance, atmospheric layers can really distort and weaken signals. Normally, systems transmitting from GEO rely on high-power radio frequency equipment, often needing hundreds of watts just to overcome losses, but in this case, the use of a tightly focused optical beam allowed efficient transmission without the typical power demands of RF systems. Another reason this result stands out is the comparison with performance expectations. While modern satellite networks like Starlink deliver speeds around 60 to 70 megabits per second using large constellations of low-altitude satellites, this test produced speeds several times faster from a single spacecraft. So, the breakthrough suggests that GEO platforms, long considered too distant for efficient high-speed optical communication, may now actually be capable of matching or even surpassing systems that rely on larger numbers of satellites. The key to this achievement lies in an advanced optical system designed to overcome atmospheric distortion, which normally disrupts long-distance laser signals. The core of the system uses a dual approach known as AO-MDR synergy, a combination of adaptive optics, or AO, and mode diversity reception, or MDR. Adaptive optics is the first layer of correction. When a laser beam travels through the atmosphere, turbulence distorts the wavefront, bending it in unpredictable ways. To fix this, the system employs 357 micromirrors, each one adjusting in real time to reshape the incoming beam. These mirrors compensate for the constantly changing distortions, restoring the laser wavefront to a cleaner, more coherent form before it reaches the decoding system. However, AO alone can't eliminate all distortion, especially for a signal traveling from 36,000 kilometers away. That's where mode diversity reception becomes critical. Instead of treating the incoming signal as a single beam, MDR separates it into several spatial modes using a multi-plane light converter. In this experiment, the signal was divided into 8 channels, each representing a different distorted version of the original wavefront. A real-time analysis algorithm then evaluates the quality of each channel and selects the 3 clearest ones. These channels are merged to reconstruct a more stable and reliable signal. According to the technical analysis reported by Interesting Engineering, this approach increased the usable signal rate from 72% to 91.1%, meaning far less data was lost to atmospheric interference. And because laser communication operates with extremely narrow beams, it avoids the spectrum congestion issues common in traditional radio systems. This allows much higher data capacity without needing those large bandwidth allocations. The implications of this result go well beyond high-speed internet. A successful 1 gigabit per second link from geostationary orbit using minimal power demonstrates a new direction for satellite communication architecture, one that could influence global connectivity models, scientific operations, and deep space mission planning. For global broadband systems, this achievement suggests that future networks may not need thousands of satellites in low Earth orbit to deliver fast speeds. Instead, a smaller number of advanced GEO satellites could provide wide area coverage with fewer launches, less orbital congestion, and longer operating lifespans. Because GEO satellites remain fixed relative to Earth, They can serve large regions continuously without the complex handovers required in fast-moving LEO systems. Another area affected by this advancement is scientific data transmission. High-speed optical communication is ideal for upcoming lunar missions, planetary exploration projects, and observatories that require rapid downlink of large datasets. If a laser can maintain a stable connection at 36,000 kilometers, the same principles can be adapted for spacecraft operating around the moon or in deep space, where traditional radio systems struggle to provide high bandwidth. Energy efficiency is also important. A 2-watt optical transmitter drastically reduces the power demands placed on a satellite. This allows more of the spacecraft's energy budget to be used for instruments, onboard processing, or extended mission durations. It also simplifies thermal management, since lower power systems generate less heat. Finally, laser communication enhances resilience. Optical links are more resistant to interference, rely on a cleaner spectrum, and offer precise point-to-point connections. This can improve reliability during environmental challenges, such as atmospheric fluctuations or crowded radio environments. This breakthrough proves that high-speed laser communication from geostationary orbit is now a practical reality. Achieving 1 gigabit per second from 36,000 kilometers with only 2 watts shows how far optical technology has advanced and how efficiently future satellites may operate. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. And don't forget to leave a comment below. Thank you for watching. See you next time.